In this lecture, we're going to talk about a mathematical concept called function composition. And what we're doing here is we're looking for a way to take a situation where we have two functions and we're doing them in sequence, right? One and then the other. And I want to come up with a way to combine these two functions into one. All right, so let's look at an example here to kind of motivate what I'm talking about. Suppose I want to find the momentum of a 1 kilogram object after it's been dropped from a height of h meters. Well, there's a physics formula for momentum, but it doesn't use height, it uses velocity along with the mass. So because my mass is 1, right, I can go ahead and put 1 in there for m, and I get this formula for the momentum. And that's nice, but like I said, it's velocity, and I want to do this in terms of height. Well, there's another physics formula, this one over here, that tells me what the velocity of an object is after it's dropped from a height of h meters. It's this thing here. And this g variable, that's the rate of acceleration due to gravity. It's a constant. It's 9.8 meters per second squared. So if I substitute that in here for g, I get this as the formula for the velocity. All right, so let's look at how I can answer a question with this. Let's say I want to know the momentum after an object is dropped from a height of 1 meter. All right, well, I can find the velocity. V of 1 is the square root of 19.6 times 1, which is 4.43. And now that's v, right? So I can put that into the momentum formula and get that the momentum of an object moving 4.43 meters per second is 1/2 4.43 squared, which comes out to 9.81. Right, so you see what I'm talking about here, right? I have to do this in 2 steps. And I've got some more numbers here for us to look at so we can see what's going on. You start with the h value, and you substitute that into the velocity formula, and that gives you your velocity. Then we go to the second step in the sequence. We take this velocity number, substitute it into the momentum formula, and I get the momentum. So we're doing this over and over again, right? If I want for a height of 3, that gives me a velocity of 7.67 meters. Put that into the momentum formula, and we get 29.41. Okay, well this is okay, right? It works, but it's awkward. It's time consuming. It's doing 2 steps where I'd really, ideally, like to be able to do this in one, going directly from the height to the momentum. And we can do this if we just kind of go through this process, but using the formula instead. If I start with h, then the velocity is the square root of 19.6 h. And now I'll substitute that into the momentum formula, and I get that the momentum is 1/2 the square root of 19.6 h squared, which simplifies to, what do we get, 1/2 times 19.6 h, which is 9.8 h. So see, what I did here is now I have a new formula. Now instead of having h go into v and then v go into rho, I have the density of h is equal to 9.8 h. All right, so this is what I'm talking about when I talk about the composition of functions. I took the formula for one function, substituted it into a second function in order to get a third that kind of takes out that intermediate step. So we have a notation for this. It's this kind of this big circle. And the way we would read this is f of g of x. And you can see there's two ways we can write this. Sometimes we'll use this big circle. Sometimes we'll just write it this way. And I actually will probably use this second version more often than the first, because I like this one because it really emphasizes that really this is just a substitution situation. I'm taking the formula for g of x and substituting it into f of x. All right, so let's look at an example here. I have these two functions, f and g, and I want to find f of g of x. Well, it helps really to think of this as f of g of x. And now we'll just start substituting. G of x is x plus 1. And if I substitute x plus 1 into the f of x formula, I get that this is x plus 1 squared plus 2. And of course, we can multiply this out. This is x squared plus 2x plus 1 plus 2, which is x squared plus 2x plus 3. All right, so now let's try doing it the other way, right? Let's look at g of f of x, and we're going to think of this the same way. This is g of x, g of f. F is x squared plus 2. And I'm going to take this x squared plus 2 and substitute it into the g formula. So this is x squared plus 2 plus 1, which is x squared plus 3. All right, now I want you to take a close look at these because we're seeing a really important thing here. Notice that the results were different, right? I got x squared plus 2x plus 3 on one and x squared plus 3 on the other. So this illustrates a really important point for function composition. It's not commutative. Remember, commutative is the rule that says we can switch the order. F of g is not necessarily equal to g of f. All right, so let's look at a quick example here. Suppose you're purchasing a car, and the salesperson offers you a $300 discount, or if you pay cash, you only have to pay 95% of the list price, which is 5% off. All right, so let's come up with two functions here. All right, the cost after the discount. Let's call this C of P. P would be the price, the list price, is P minus 300. Then on the other hand, right? Let's look at the other option, the cost based on, let's see, what can we call this? Let's call this the cost as a percentage of the price is 0.95 P. All right, so now I've got two functions, right? Two functions, one for each of the two scenarios. So now let's look at this situation. All right, suppose you convince the salesperson to give you both discounts. Right? I want to come up with a new function that it tells me what the cost is based on the list price, P, if both discounts are applied at once. So let me put my discounts up here again. The first one was P minus 300, and the second one was 0.95 P. Okay, well, hopefully you realize from our last quick example there, the first question you have to ask is, in what order are we going to do these? Because it matters, right? And let's actually do it both ways, so you can see how it matters in this situation as well. The total cost of P is equal to, let's do D first and then the percentage and see what happens. So this is C of 0.95P. Right? I just substituted 0.95 in here for the cost function. And now I'm going to substitute again. I'm going to go to the d function. I'm going to replace that p with 0.95p. And there we get one possibility. Right, 0.95p minus 300. Now let's go the other way. Right, let's look at the percentage and then the discount. So this would be what? This is the percentage. The discount price, that's p minus 300. Just substituting again. And now putting this into the percentage formula, this is 0.95 times p minus 300. So let's multiply this out, right? So it kind of looks like the other one. This is 0.95p minus 285. So you see, well, clearly, once again, right, we did get two different functions, right? The result is different depending on the order in which we do these.